So today in this lecture we are going to discuss about the concept of the torsional undamped vibration. As the name indicates, it is undamped. We are not taking into consideration the damper. And second, it is a case of a torsional vibration. There is a deflection will be in the terms of theta, not in the terms of x. Now you can see the diagram. This is a disc which is attached to a beam. Now if we provide a twist of theta angle in this direction, as you know from the Newton's second law of motion, if we apply a deflection in a certain direction, there will be an inertia force which will try to bring the body back to the mean position. So for this case, this will be the inertia force. Just like for a spring and mass system, if this is spring, this is a mass, if we displace the mass in this direction x, the mx double dot will try to bring the body back to the mean position, inertia force. So if we provide a theta deflection in this direction, so in the opposite direction, here the inertia torque will come into play. It will be I theta double dot. Keep it in mind, in case of linear vibration, inertia force will be mx double dot, and in case of the torsional vibration, inertia torque will be I theta double dot, and both will act in the direction opposite to the direction of the displacement. Fine. Now this is the done. Now this beam will possess a stiffness, which stiffness is called as the KT. Just like here we are having a stiffness K, and here this is getting twisted, so it is having a torsional stiffness which is denoted by KT. Fine. Now KT, we understood what is the value of KT. KT is defined as the ratio of T upon theta. What does it mean? Torsional stiffness is the ratio of torque per unit theta. Fine. It is the ratio of what? Torque required for producing a unit angular displacement in the direction of the force. तो KT क्या होता है हमेशा? T upon theta. It is a torsional stiffness. So KT is clear. It is a torsional stiffness. It will come only in the picture when there is a case of the torsional vibration. And I theta double dot is the inertia torque. Now for this kind of numerical in which we are having the linear vibration, if we apply the D'Alembert's principle, what is the statement? The statement is the submission of the inertia force plus submission of the external force equals to 0. This is the statement. Fine. And for the case of the torsional vibration, the statement is what? Submission of the what? Moment of the inertia plus submission of the moment of the external force equals to 0. Fine. So here we can also state that this statement as submission of inertia torque plus submission of the external torque equals to 0 in the simplified language, just like this: inertia force plus external force equals to 0 for linear vibration, and for the torsional vibration, inertia torque plus external torque equals to 0. So by this method, if we find out the natural frequency of this system, what is the inertia torque here? I theta double dot. That will be always be positive. Why it is always positive? Because it is directed towards the mean position. आपने displace इसको clockwise किया है, so ये anti clockwise direction में act करेगा, so as to bring this disc back to the mean position. And what is the external torque? Is the KT into theta, because this is the torque, so torque will become what? KT into theta. That torque is of the beam having stiffness KT, so it will become KT theta. Now if we compare this equation with the theta double dot plus omega n square theta equals to 0, what we will get? Suppose I am shifting this I in the downward direction. Fine. So I will get, after comparing these two equations, what I will get? Omega n as the under root of kt upon I. Fine. And for this kind of equation, I know what is my inertia force, mx double dot. What is my external force? External force is nothing but the spring force kx. It will be kx equals to 0. So if I shift this mass in the downward direction, so I will get omega n as under root of k by m for a linear vibration, omega n as under root of kt by I for the case of a torsional vibration. This is the basic difference between the torsional and the linear kind of vibration. Hope the concept of torsional undamped vibration is clear to you. So in the next lecture we will solve a numerical related to torsional undamped vibration, and I want to make it clear that if in some numerical, this is called as a linear spring, we will find a spring like this. This is nothing but a torsional spring having stiffness kt. So what is the value of torque of this spring? Torque is nothing but kt into theta. Fine. So hope this session or this lecture is clear to you, and we will meet in the next lecture related with the numerical on the torsional spring. Till then, watch this numerical, make your basic clear, and thank you.